Okay, welcome to Lecture 3, Equilibrium in 2D and 3D. Today, basically I'm going to work a bunch of examples in 2D and 3D. I kind of decided that I wasn't going to do a formal presentation of how to do 3D. I was just going to kind of work some. And so we'll see what happens. I'm going to apologize ahead of time. My dog seems to be going crazy. So if you hear any growling or whining, that's Rocky's fault. Anyway, so we're just going to work some examples today. And I got these from your book primarily because, I can't make these up. And some of these I can't even draw very well. Okay, so here's the problem right here. And here's what we're given. We've got some kind of bolt, and it's got 4 forces on it. 4 forces applied to the bolt: F1, F2, F3, F4. And what the required is, I changed the required a little bit, but it says determine the force required to keep the bolt in place. Okay, the actual question was determine the resultant of these 4 forces. However, I changed it to determine the force required to keep the bolt in place because that just makes me happier. Okay, so what we're going to do for this, and this is the way that you should solve all these. By the way, this is how you should do your homework. Show the given, show the required, and then show the solution. If the given has a diagram, you have to draw the diagram. Okay, I know you don't want to, but draw it. Okay, so for the solution, what we're going to do here is I'm going to draw a free body diagram. And the key here is to think about what it is that I'm drawing the free body diagram of. Okay? And so the first thing is I'm going to draw a free body diagram of the bolt. Okay, so it's going to look like this. Okay? And so that thing that I just drew is the free body diagram, is the thing that I'm going to draw the free body diagram of. Which is nice because it's pretty easy to draw, right? It's like this. Okay, by the way, you do have to do this. On a test, I will either tell you that you have to do it or you don't have to do it. But if it's worth points, I'll tell you to do it. But on a test, you don't have to do given required solution because you may run out of time. Okay, so this is free body diagram. So that's the body. And it's free, maybe, so I need to draw the forces on it. Luckily, this free body diagram is pretty easy. So this one's 150 newtons. And that's going to be F1 equals 150 newtons, and that's at 30 degrees. Okay, and then I've got F4, which is going to go off this way, which is going to be 15 degrees. Okay, and that's F4 equals 100 newtons. Okay, F3 is going to be straight down. We like F3 because F3 is going to be fairly easy, 110 newtons. Okay, and then I've got this last one, which is at 20 degrees from vertical. Okay, so this is vertical. And we're going to call this 20 degrees here, and that's going to be F2. And that equals 80 newtons. Okay, so you're saying to yourself, good, we're done. No, we're almost done. So the last thing is, when analyzing your free body diagram, you always have to think about the forces. But when you think about the forces, so if we go look at our image over here, and basically anywhere, so we have 2 types of problems, of forces. Body forces, so that would be weight. In this case, we don't have any information about this bolt, so we're going to assume weightless. Okay, so that's your body force. And then everywhere where we cut this thing off from the world, we have to ask ourselves, by removing it from the universe, okay, where it was touching the universe, were there any forces there, right? And so if you look right here, okay, the bolt was attached to this wall, okay, or really it was attached to this arm of the bolt. And so by being attached right there, there was a force there. Now I'm going to make an assumption here about the direction of that force, and I think this is probably a pretty good assumption. Okay, I'm going to assume that it's going off in this direction. Okay, so I'm going to call this, it's the opposite of the resultant, right? Let's just call this F bolt. Okay, and we don't know really anything about that bolt. Okay, I know it's got an angle, which I'm just going to go ahead and call theta. Okay, and I'm guessing its direction. Now, if it comes out that I have the wrong direction, then that means that some of my signs are wrong. Okay. And maybe at the end, maybe if there's time, I'll come back and I'll resolve this, making an incorrect assumption. Actually, you know what? Let's make an incorrect assumption. Okay, and that'll kind of just show us what happens here. So let's make an incorrect assumption right off the bat. Okay, because I don't want to stress you out about the idea, the importance of this assumption, because sometimes it's not so obvious. Okay, in this case, it seems pretty obvious. I'm going to go ahead and do what my statics teacher did. I'm going to assume that it's both positive in x and y. Okay, so I'm going to call this F bolt, force of the bolt, and it's got an angle here, which I'm going to call theta. Okay, now one of the things that I like to do, and so we kind of have two ways that we work these problems, is that we typically either do them with triangles or we do them by components. And in this case, what I'm going to recommend to you is that, I mean, I can't say that this is always the case, but in this case, we've got 5 forces. When you have 5 forces, you can't really make a triangle, right? A triangle is going to make nice with 3 forces. When you have 5 forces, it's not really going to work out very well. So I'm going to recommend that we do components for this. Okay, and so what we're going to do is we're going to split each of these forces into its x and its y. Hey, I just walked you. Hold on, I'm going to play with the pup for a second. Okay, and before we delve into the components, I want to spend a little bit of time and I want to step back and I want to remember our trig tools, okay? And these are the tools that we're going to use whenever we're dealing with angles and sides and all kinds of stuff. And this class has, let's face it, quite a lot of trig, okay? So I'm just going to try to keep rewriting this until it kind of gets into your head, okay? So there is the any triangle, which is any old triangle whatsoever. And so that any triangle looks like this. It has the angles or whatever they are. It has sides A across from which is alpha, angle alpha. It has side B across from which is side beta. And it has side C across from which is angle gamma. Okay, conversely, we have the right triangle, okay, which has one of these angles is a right triangle, and this is C. And this, well, either one of these can be A or B. And these are angles where this is angle alpha and this is angle beta. Okay. So with SOHCAHTOA, I've kind of circled in red here because I think of SOHCAHTOA as kind of being the most important thing in all of trig. Well, I mean, it is because it's the basis on which trig comes from. Oh, if you hear any cracking noises, that's because I gave the dog a giant stick and he's destroying it as we speak. So you might hear some cracking noises. It's just going to make a mess. All right, anyway, so these are the things we're going to use for our trig tools. Okay, so we're going to zoom back over here, and we're going to keep in mind our trig tools as we try to break these things up into their components. Okay, so I'm going to go one force at a time, and I'm going to start with F1. I'm just going to go in order. Okay, F1 equals. Okay, so this is going to be the whole force. I'm going to split it up into its components. So in this case, we're on a coordinate system that is x, y, okay, and the z is unimportant, okay, because this is a 2D problem. So F1, so basically I'm going to draw my first component in the x direction, right here, okay, and the next component is going to be in the y direction, okay, so this will be F Fy1 or F1y. Let's call it F1y, and we'll call this one F1x. Okay, that seems to make sense. Okay, so we need to get the sides of this triangle. I know the hypotenuse here is 150 newtons. Okay, and if I want F1y, okay, so if I'm using this angle 30, then F1y is going to be, well, let's see, let's do our little SOHCAHTOA. So we know the hypotenuse. So if we know the hypotenuse, it has to be sine or cosine. And in this case, it is the angle opposite the 30 degrees. So SOHCAHTOA, so it's sine. So I can say the sine of 30 degrees equals F1y over Fy. Okay, and these are magnitudes. Okay, so I can resolve for F1y, and I can say F1y equals, okay, or the magnitude of that one, equals Fy times the sine of 30. Okay? Now I'll note that if I wanted to do f1x, okay, I would end up with the cosine of 30 equals f1x over the hypotenuse, which in this case is f1. Okay, it looks like up here I made a little typo. So let's delete that. This should be f1, and this should be f1. Okay, there's no fy, f1, and f1. Okay, noting that the magnitude of f1 is 150 newtons. Okay, so I could rewrite this one on the bottom as f1x, the magnitude of that is f1 times the cosine of 30. Okay, so these two things are going to help me solve for my f1x and my f1y, okay, for the magnitudes. Okay, so f1x, then if I plug this into the calculator and I plug in 150 Newton, well, you know, I don't want to really write all over my trig tools. Okay, well, whatever, it's too late, we already did it. Okay, so if I plug that in, then into both of these locations, okay, then I get for my f1x and my f1y, okay, I get, well, it should be, you know, 75. Okay, this is going to have the units of newtons. Okay, and then for f1, excuse me, that's, yeah, sorry, 75 newtons, right, that's my y. And then for my x, okay, so there's some bookkeeping here. For my x term, okay, it's going to be cosine 30 times 150, so 150 cosine 30, okay, and I get 129.90. Well, unfortunately, there's not much space there, 129.90. Okay, again, always remember, I keep, that's disgusting, Rocky, at least 5 sig figs, okay, throughout the problem. Okay, so that's f1. Cool. All right. Now let's see what we can do for f2. Okay, f2 equals. Okay, I'll use green for this one. So let's go ahead and let's do it like that. Okay, so it will match up here. All right, so again, let's see. I'm going to go here like this. Okay, and then I'm going to go this way right here. Okay? So the sides, similar to what happened over here, okay, we're going to do some SOHCAHTOA. Now again, we know the hypotenuse here is 80 newtons. Okay, so we're going to be working with sines and cosines. Here's my 20 newtons. So the one across from 20, okay, that's the opposite. So this one is going to be using the sine. This is the adjacent, so it's going to use the cosine. Okay, so we will go ahead and I will say, all right, so f2 in the x direction, okay, the magnitude of that one is going to end up being, and if you can work this trig out, right? You know what? I'll work one more set of trigs out, and then I'm going to expect you to kind of play with that on your own. Okay, so well, let's just erase all this. Okay, this will become second nature to you eventually. All right, so let's do the x term first, okay? So that's this side right here, okay? And this is going to be, that's the sine, because it's the opposite side. So sine of 20, okay, equals the opposite, which is going to be f2. So this side is f2 in the x direction, magnitude, over the hypotenuse, which is just f2, okay, the magnitude of f2. Okay, so if we rearrange that, I get f2x, the magnitude of that, equals magnitude of f2 times the sine of 20. Okay, if I plug in 80 newtons right here, okay, I'm going to get f2x equals, okay, 26.362 newtons. Okay, similarly, I could do the cosine of 20 degrees equals f, so the cosine, we're going to deal with the adjacent. So that's this side right here. Okay, so this is f2y. So f2y over the hypotenuse, which is going to be f2. Okay, So rearranging, f2y equals f2 cosine 20, like that. And we'll end up getting that, so if I plug in 80 for the hypotenuse, then I'll get f2y equals, okay, getting really sloppy here, but f2y equals 75.175 newtons, okay? So if we keep our x's and our y's, if we keep our ducks in a row, okay, the x term is 27.326 newtons. And I note that I forgot a unit on the line before, which is no good. So we're going to squeeze a little newton in there. And then that's going to be I. And then J is 75.175 newtons. J. Okay, now I need to check the directions because, well, I put positive signs there. That is a mistake because we need to check them before I draw them in there. So let's see here. In the I direction, in the x direction, I, which is the x direction, this is negative. So we've got negative in the x direction, and in the y direction, we've got positive. Okay? All right, so now we're going to do F3. F3, let's use blue, because let's just get a new color. F3 is also the easiest one. Okay, so F3 is straight down, so it is 0 in the x direction. Okay, and it is negative, because it's down in the y direction, 110 newtons in the j. Okay, and then let's see, F4. Ooh, F4. Okay, let's see if we can find some space to do F4. I'm not going to do all the trig on this one because it's the same trig as what we did for F1, and so I could say that F4 x. Okay, the magnitude of that is going to end up being the magnitude of F4 times the cosine of 15 degrees. And I could say that the magnitude of F4y equals F4 sine of 15 degrees. Okay, and if you're not that great at trig, I highly recommend that you go through it and make sure that you can make that make sense to you. Where in this case, F4 is 100 newtons. So if I plug in 100 newtons right here, and I plug in 100 newtons right here, okay, I'll get F4, oh, that's a 4. Excuse me. F4x, the magnitude equals, and F4y, magnitude equals. All right, these numbers here, so 96.593 newtons in the x direction, and 25.882 newtons in the y direction. Those are the magnitudes, okay? So if I'm going to go over here and I'm going to add them to, the dog is getting restless again. So I'm going to add these to our things. So the x term is 96.593 in the I direction. I need a little arrow. And that is in the positive direction, because if we go up here, that's in the positive x direction. So that's positive. Oh, I need a newtons. Okay. You got to keep your units. A lot of people don't like to do this. I'm going to force you guys to do this because I'm a jerk. All right, but then in the y direction, it's going to be negative, okay, because you can see that that's going down. Okay, so we'll go minus 25.882 newtons in the j direction. Okay, cool, right? All right, now we need the force of the bolt. Okay, and you're like, well, how do we get at that? You know, we don't know anything about it. Right, exactly. So the force of the bolt, okay, equals force of the bolt in the x direction, okay, times I like that, plus the force of the bolt in the y direction times j. Okay, so that's how we do it. Okay, and you're like, wait a second, but we don't know what any of those things are. We're right. But we know that this thing's not moving, right? So because it's not moving, I'm going to add up all these forces with the knowledge that, okay, this thing is at equilibrium. Sum of the forces in the x equals 0. Sum of the forces in the y equals 0. So if I add up all of these forces, they should add up to 0, right? And note that this column with all the i's, let's see, I can't really draw it, but yeah, I can kind of draw a little dotted line here. Everything to the left of this dotted line, those are x forces, so they have to add up to 0, right? Okay, so I can say, so I can take all of those forces and I can add them up, and I can say the sum of the forces, okay, equals, and it's going to be FBX plus, now I'm going to add up all these numbers in this left-hand column here. So I'll add 129.9 minus 27.362 plus 96.593 equals. Okay, so this is plus 199.13 newtons. Okay, that's the I. Okay, plus, now I'm going to add up all the J terms, which is going to be FBY plus all the other terms. So I'm going to start doing that. So it's going to be 75 plus 75.175 plus, minus 110 minus 25.882 equals, a small number. Okay, 14.293 newtons. Okay, J. All right. So what I'm now going to do is I'm going to apply this right here because we're at equilibrium. So in other words, the sum of f of x in the sum of forces in the x direction right here has to equal 0, and the sum of the forces in the y direction here has to be equal 0. So what does that mean? Well, that means that FBX equals, okay, negative 199.13 newtons, and FBY equals negative 14.293 newtons. Okay, so what do these negative signs mean? Okay, and this is kind of an interesting thing. So if we go back to the beginning, when I told you, well, I knew that this force was actually going to be off in kind of this direction, right? I told you, I said, look, I think it's going to be off in this direction, right? It's going to be in that quadrant anyway. And I chose it to be in this direction. So you're thinking the negative signs are telling me what direction this force is. And that's not the case. The negative signs are telling me that the direction that I assumed is incorrect. Okay, so I assumed it was up here, okay, positive x and positive y, and I got a negative x, which means it's the opposite of the x I assumed. I assumed positive, so it gave me negative. And it gave me a negative y, which means I assumed a positive y, and it's actually a negative y. So if you get a negative sign, it's the opposite of what you assumed. Okay, so for me to make this simple, usually what I do is I assume that my forces are in the positive x and the positive y. That just makes things easiest for me. Okay, and that way, this will end up doing both of those things for me. Okay, but this is not what the question asked, right? It said the force required to keep the bolt in place. I got two forces. It kind of wants one force. Okay, so basically I got a triangle and it looks like this. Okay, I've got 199.13 newtons going this way. Okay, and I've got, so tip to tail, 14.293 newtons going that way. But it wants just one force. So it wants the resultant here to keep that thing still. Okay, so this would be the resultant. Okay, and it looks like this. Okay, now how do I get that side of that triangle? Okay, well, let's go up to our trig rules. Okay, that's a right triangle. So I can use the Pythagorean theorem, and I can use SOHCAHTOA. I don't have to use these. I can use the other ones, okay, if I want to, if I need them. Okay, so we're just going to see what we need. All right, so let's go down here. Okay, so the first thing I want to get is I want to get the size, the magnitude of this side. And on a right triangle, the easiest way to get that is to say, well, c squared equals a squared, 199.13 newtons squared plus b squared. Okay, 14.293 newtons squared. Okay, if I solve this, I will get 199.64 newtons. And then the other thing I need is, okay, so this is the bolt or whatever, and I need to get this angle, theta. Okay, so to get that angle, theta, well, let's see. I need to think trig again. And I've got two sides. I've got this side, which is the opposite side. This is the hypotenuse over here. So this is the adjacent. So I've got the opposite and the adjacent, so that's tangent. So the tangent of theta equals the opposite, 14.293 newtons, divided by the adjacent, 199.13 newtons. Okay, note that we should expect this angle to be very small. So what we're going to do here is to both sides, I'm just going to draw it like this, like I'm doing it to the whole equation. So to both sides, you take the inverse tangent. So theta equals the inverse tangent of 14.293 newtons divided by 199.13 newtons. Okay, so theta equals, okay, 4.1055 degrees. Okay, noting I keep 5 all the way through, and what I'm ultimately going to do is I'm only going to report 3. So when I report my answer, I'm going to say, well, I called this C up here, but really I guess we should have called this FB. Okay, so FB then is, so I'm only going to report 3 significant digits, so that's going to be 200 newtons. Come on, buddy. 200 newtons at an angle of, like that, 4.11 degrees, okay, south of west. Okay, so that would be how you would solve this, okay? Now, I will note that things can be a little bit easier if, when you're solving this, you make all of your angles with either the horizontal or the vertical. So like in this case, you could have come in right at the beginning and you could have said, okay, this 30-degree angle is with the horizontal, this 15-degree angle is with the horizontal, there's 20-degree angles with the vertical. And you might have said, you know what, I don't want to deal with that. I want all of my relationships to be easier. And so I'm just going to use this 70 degrees over here and drop my lines this way. You could have done that, okay? And that would probably make things a little bit easier. But, you know, you'll get a chance to do that, okay? So let's see here. And let's zoom over here, and we're going to do the second problem. And it looks like we're probably going to have time for 3 of these. Okay, so again, we're going to start here with given. Okay, here we go, given. One last thing. So over here, okay, I could have used some trig, but I think if you can imagine what this would have looked like ultimately, if I tried to do tip to tail for all 4 of these, like it would have looked like this, F1, and then F2 would have gone this way, F2, and then F3 would have gone straight down, F4 would have gone this way, right? And then the force of the bolt would have gone back this way. Force of the bolt, right? Because they would have all summed to 0, so it would have all come back to this point. Okay, that would have been very, very hard to solve this using just triangle rules. Okay, because all these angles would have been very, very complicated. So if you have too many of them, I highly recommend you break them up into components and do it this way. Okay, it's just a lot of bookkeeping. Okay, anyway, so if we're going to go back over here, and here we go. Given, we've got some automobile, it's being lifted onto this boat, and as it's being lifted, this little man, I called him a tiny man, so this tiny man here, he attached a rope here to that ring, and he's pulling it off to the right for some reason. Okay, I don't really know why he's doing that. But the car weighs 3,500 pounds, which seems kind of heavy for that little car. Anyway, so we're going to solve this sucker. And we're going to, okay, and so what we're going to do is we're going to make note of the fact that right off the, so anytime we solve forces, or we sum forces, we're going to have to do a free body diagram, okay? So I'm going to start knowing that this is statics class. You almost always need a free body diagram. And the key is this car is not moving. So if the car is not moving, then that means that the sum of forces in the x equals 0, and the sum of the forces in the y equals 0. Oh, last thing I should note. These are 2 equations. If you have 2 equations, how many unknowns can you solve for? 2, okay? Over here, we had 2 equations, sum of f of x equals 0, sum of f of y equals 0. So it means we solved for 2 unknowns. These 2 unknowns were, depending on how you look at it, it was f of bx and f of by. Okay, we were able to solve for them. We solved for 1 out of each equation. Or you could have looked at it from the beginning and said it was FB and theta. Okay, and so those came out of some more work. But so we can solve for 2 unknowns here. If we were in 3 dimensions, you could solve for 3 unknowns. Okay, so just kind of be aware of that, because that's definitely going to come up. And eventually we will get 6 equations, and we'll be able to solve in 3 dimensions. We'll get 6 equations, and in 2 dimensions we'll end up with 4 equations. But we'll get there. Okay, so all right, so we need to do a free body diagram, okay, to solve this. Okay, so here's a free body diagram. Now the key here is what do we want to know? And what we want to know is the tension in this rope. Okay, so this is the rope pulling off in this direction. So one of the things in our free body diagram needs to be that tension. It doesn't have to, I guess it doesn't have to be, but it's usually helpful. Like that's usually a good thing to have, because because then you can solve it. Sometimes you can't go directly for what you want. So I'm going to do this just like I did it last time. Okay, I'm gonna draw the free body diagram of this ring. Okay, we're going to assume it's weightless. Okay, assume weightless. Okay, because we don't have any information on it. And it's highly likely that the weight of that ring is not really all that important here. Although, truthfully, it's kind of amazing that this one little man, this tiny man, is like pulling that hard. Anyway, so I'm going to do a free body diagram of that ring. I'll draw the ring in blue, because, blue is my favorite color. Unlike Aerosmith, I think their favorite color is pink. Okay, so now we've got forces. Okay, so everywhere where that ring comes in contact with the rest of the universe, we have to have a force. Okay, it's weightless, so we're not going to deal with the body force, but we're just going to do surface force. So anywhere where that ring comes in contact with the world, we're going to replace that contact with a force. So the first thing we've got is a force going this way. Oh, I chose red. I'm not really a fan of red, but whatever. Okay, we'll note that this angle here is 2 degrees. Okay, because this angle is 2, so that angle is 2, so that's alternate interior. So this is 2 degrees. Okay, and so that's 1. So we'll call that the tension in the cable. I'm just going to call that tension in the cable, TC. Okay, now note, we don't know TC. We know its direction, but we don't know TC, which means that, that's 1 unknown. Okay, now the car, we have the weight of the car right here, weight of the car. Okay, which is known as 3,500 pounds or 3.5 kips. And we know, so kips is a kilopound, and we know that this little man is pulling off in this direction. Okay, I guess he's a tiny man. I keep calling him a little man. Anyway, so going this way, so that's 30 degrees. Okay, and we'll call that tension due to the man. Okay, notice we have 2 unknowns here. Okay, I know the weight of the car, and I don't know the tension in the cable, and I don't know the tension from the man. Okay, let's hope he's really not that tense, because then he should try to relax, do some yoga or something. All right, so I'm going to work this in white, because that red really is a horrible color. Come on, punk, give me white. All right, so here we go. So now over here, I highly recommended that you do the components, and I'm going to do the components on this one in a second. But the components is not really the quickest way to do this. Let's go ahead and do the components, just so that we can kind of keep that. So we're going to do this 2 methods. Okay, and the first one I'm going to do is we'll do components right here. Okay, so and I'm going to show you how this can get a little bit easier doing components if you do all of your angles with respect to the same axis. So I'm going to go right here. I'm going to do my axis here. So that's 88 degrees. Okay, so cool. All right, so now we're doing our triangles, right? And so now both of my triangles have to do with the x-axis. And so if I start with, let's start with TC. Okay, so TC looks like this. Okay, as best I can draw it. Okay, here's the x component. Here's the y component. Okay, here's an angle of 88 degrees. Okay, here's a right angle. Okay, let's zoom in there. Okay, so here's, so this is TC. We don't know TC. Okay, if we do our trig, okay, if we do it and we do it properly, okay, this is the opposite side. TC is the hypotenuse. Okay, so if I want this side, this vertical side, then I have to say to myself, okay, well, that vertical side is going to be, let's see, it's going to be the sine of that angle, 88 degrees, equals the opposite side, which I'm going to call TCY, divided by the hypotenuse, which is TC. Okay, rearrange, and I'm going to get, let's see, TCY equals TC sine 88 degrees. Okay. So now I'm not going to do the trig for the x, but if you don't know the trig, I recommend you do it. Cosine 88 degrees. Okay. Anyway, so what we're going to do down here then, if I'm doing components, then I'm going to show all of my things lined up. So this is TC equals magnitude of TC cosine of 88 degrees. Okay, that's in the I direction, plus the magnitude of TC times the sine of 88 degrees. Okay, that's in the J direction. Okay, now we have to think about those signs before we move on. Okay, the X direction is negative, so I need a negative sign in there. If I can get this thing to erase. It really hates me when it comes to erasing. Oh, there you go, it erased. Hello, my friend. You're erasing punk. All right, equals negative. Okay, positive. So in the Y direction, it's going up. In the X direction, it's going to the left. All right, so that's TC. Okay, I'll show you in a second why this makes things easy to have all your angles with respect to the x-axis. All right, so then TM, okay, over here, okay, that looks like this. Okay, so this is TMX, this is TMY, and this is TM. This is TM, and this is the angle we're working with, 30 degrees. Okay, if you do the trig, what's going to come out of this is TM x, magnitude of that equals TM cosine 30 degrees, and TMY equals TM, the magnitude of TM, times the sine of 30 degrees. Okay, and again, if you can't see that off the top of your head, work the triangle. Okay, so what ends up happening here is we get TM equals, okay, we're going to get magnitude of T, oh, that's not what I wanted. Oh yeah, this is the tension of the man. Okay, I need to remember that. You know, this is probably the man trying to hold y'all down. So don't show him any love, right? He's holding us all down. And we're not a fan of being held down. Okay, TM, okay, cosine 30 degrees. Luckily, he's a tiny man, so we can overpower him. Okay, and then TM. Oh, these all need arrows. Sine 30 degrees. Okay, J. All right, so there you go. And let's get our signs on here. It is in the positive X direction, and it is in the negative Y direction, okay? Because we can see that looking here. So this is the positive X direction and the negative Y direction. Okay, so you should note the pattern here if you do this correctly. You notice we have sines here. We have the angle with the horizontal, and this is the hypotenuse, okay? We have cosines here. This is the angle with the horizontal, and this is the hypotenuse. So if you always use the same, like if you do all the angles with the horizontal, then you will end up with all cosines here, and you'll end up with all sines here. If you do all angles with the vertical, then what would end up happening is you end up with all sines here and all cosines here, okay? Or you could just redo the trig each time. I redo the trig each time because I've gotten really good at trig, and I highly recommend that you get that good at trig, because what happens to a lot of my students is they decide they're always going to do all the angles with the horizontal, which is fine, but then they forget how to do the trig, and then they get to a later class like fluid mechanics or structures or something, and the angle isn't with respect to either the horizontal or the vertical, and you have to twist it. You have to twist your coordinates into something unusual, and they don't know how to do it. Okay, so I recommend just learning how to do the trig. That's really the best way to do this. Some of you will shortcut it. It may work out for you, it may not. My guess is usually not. So, or it'll bite you eventually. All right, so we got a third force here. We got the weight of the car, which of course is the whole point of all of this. And so the weight of the car equals, well, it's only in the j direction, so it's negative weight of the car, j. Okay, cool. All right, so we're going to work, I guess we're going to work sideways here, okay, because I have to plug in these values. Oh, wait, we don't have TC, do we? Oh, that's interesting. So we don't have to plug in the values. Let's plug in one value here. Let's delete here. Where is this? Let's plug in one value, and of course it hates when I try to erase. It'll probably erase like 5 minutes from now. Oh, there it goes. All right, woo, all right. All right, 3,500. So we'll put in our number right here, 3,500 pounds. Okay. All right, so we're going to add all these suckers up, and I'm going to get TC, the magnitude of TC, cosine 88, plus magnitude of TM, cosine 30. That's in the I direction. Okay, and then plus in the j direction, magnitude of TC, sine of 88 degrees, minus magnitude of TM, sine of 30 degrees, minus 3,500 pounds, j equals 0. Oh my lord. Oh my lord. This sucks. Anyways, well, equals 0, right? So now what I want to point out here is this is two equations. Okay, it looks like one, but it's actually two. Everything in the x direction has to sum up to equal 0. Everything in the y direction has to sum up to equal 0. Okay? So the way we solve this, and this is just a lot of busy math, okay? So if this happens to you on a test or something, either the problem is difficult and just kind of requires a solution like this, or you might have just done this kind of this, a not so fast way. Okay, so what we're going to do here is I'm going to take this equation right here, and I'm going to solve for TC or TM. It doesn't matter. Okay, so because remember that this is an equation equals 0. Okay, that's one equation. So I'm going to do is I'm going to solve for TC in terms of TM. So TC equals, okay, TM cosine 30 divided by the cosine of 88. Okay, so TC equals 24.815 TM. Okay. Now let's ask if that makes sense. Does it make sense to you that the tension in the cable should be about 25 times as much as the tiny man's tension? Okay, I think it makes sense. Well, I mean, I don't know if it should be 25 or 250, but if this 25, if the coefficient were on the TC, you'd be like, okay, there's no way the cable, that little man is pulling with 25 times the force of the cable. Okay, so anyway, so that's a good sign. So what we'll do then is we'll plug it in up here, okay, and then we can solve this whole problem. Okay, so let's zoom in and let's solve that, 24.815. So I've got 24.815 TM sine 88 minus TM sine of 30 degrees minus 3,500 pounds equals 0. So this is my y equation, but I've plugged the x equation into it, okay? And I'm no longer worried about the j because I'm only in one direction. So now we're going to solve for this. So what we're going to do is we're going to bring the 3,500 over, so equals 3,500 pounds, Okay, and I'm going to combine these two terms. Okay, and so there'll be a Tm here. Okay, because I'm going to factor that out. And I'm going to be left with, well, I'll just kind of write it out for you, 24.815 sine 88 minus the sine of 30. Okay, so, and then when I solve all of this, we're going to get that the magnitude of that force, 144.03 pounds. So the tiny man is pulling with 144.03. And if I want to know the force in the cable, I'll do the TC, okay, the tension in the cable, and I'll multiply 144.03, I'll plug it in right here, and I'll multiply it by 24.815. Always remember to keep at least five significant figures all the way through, and we'll end up with 3574.2 pounds. Okay, note, okay, this is slightly more than the car weighs, okay, which makes some sense, okay? So if we go up and we look up at this, at the initial drawing, okay, this thing is basically pulling upwards. Okay, it's 2 degrees off of vertical. Let's get a color that you can actually see. Okay, it's 2 degrees off of vertical. Okay, the fact that this guy is pulling on it, okay, is making it more difficult for that cable, right? Two things. One, it has to pull to the side a little bit, which it wasn't doing before, so that's extra force. And the other thing is this guy is pulling downwards on it, so he's adding a certain amount of vertical force on it. Okay, so this little tiny man, if you're that cable, you think that little man sucks, okay? Or maybe, you know, this is a friendly classroom, so you think that little man is a poo-poo head, okay? Poo-poo head. Okay, I think that works, right? Poo-poo head? Okay, anyway, I think we can all agree that poo-poo is not really a good thing. All right, so this tiny man, you know what? Maybe this tiny man has a good reason for being a poo-poo head. So we should not judge, okay? Because we love everybody. All right, so that's one method, okay? Components. Let's do another method, okay? I'm gonna do a free body diagram. Well, let's just take the free body diagram I have, and I'm gonna draw a little donut again. Okay, here's my little donut. Okay, so that's the ring. Okay, but I'm going to do tip to tail of all these forces. Okay, so right, because I know that all these forces are going to add up to 0, which means the tip to tail, if I do tip to tail all the way around, I'm going to come back to 0. Right, so I've got this little feller going up like this. Okay, got an angle of 2 degrees. 2 degrees. Okay, and then I got this little feller going back this way. Whoa, we can't go that far. Whoa, why can't we go that far? We can't go that far for good reason, okay? And that reason is we have to keep in mind what it is that we're aiming for here, okay? And what we're aiming for, if it will let me delete, which it is considering, what we have to remember here, you know what, I'm going to zoom in so that we can see this a little bit better. Oh, let's keep it here for now, okay? So what we have to remember here is that the weight of the car is straight down. So the weight of the car is right here. It's straight down. Okay? So this Tm is going back this way, like that. Okay? And it's got an angle like this, 30 degrees. Okay, so let's zoom all the way in on this sucker, because now we pretty much got everything we need. Okay? All I've done is I've taken all 3 of these forces over here, 3 forces, and I drew them tip to tail over here. Okay, and now I just have a triangle. Okay, now what's the beauty of triangles? The beauty of triangles is that when we have triangles, we can do trig. Okay, so this side is 3,500 pounds. Okay, this long side here, this is TC. Okay, and this side right here, well, that's the tiny man. Okay, the tension from the man. All right, so we're in good shape. Right, we're ready to rock and roll. Almost. So let's get there. Okay, so let's put this vertical line right here, because here's the thing. At this point, I'm thinking that if we're lucky here, so this is the x direction, this is the y direction, and I'm thinking that we can do this with some simple trig. Okay, now what would help us if we wanted to do trig is some angles. Okay, and what I'm thinking is we know one side. We're trying to get the other two sides. So let's go, let's zoom out. Let's go over here to my trig tools. Okay, this is not a right triangle. So our two options here is the law of sines and law of cosines. The law of cosines requires us to know two sides. Okay, it could be any two of the sides, but like this whole right-hand side is a side angle side next to each other. We don't know two sides, so we can't really work with that. However, this one right here requires us to know one side, but we need to know some angles. So let's find some angles. If we find some angles, we can use the law of sines. By the way, I am aware that sometimes I'm going to write this as A over sine A and B over sine B and C over sine gamma. That works too. Okay, so anyway, let's go back over here. Okay, let's zoom in on this sucker. Okay, so these two lines are both vertical. Okay, so because they're both vertical, I mean, my drawing really is not very good, but I'm not going to be able to do it any better. That's 2 degrees right there. Okay, so if this one right here is 2 degrees, and this one right here is 30 degrees, and the whole angle, this whole angle is 90 degrees, then this angle right here is 90 minus 30, which is 60, minus another 2, which is 58 degrees. 58 degrees. Okay. Interesting. Okay. So anyway, so then, and now we've got two interior angles on a triangle. All three angles on a triangle add to 180, which means that this one right here is, well, let's see, 2 and 58 is 60, so that leaves 120 degrees left. Okay, so now we can do the law of sines. So let's do the law of sines. Okay, law of sines. All right. So let's say 3,500 pounds, okay, over the sine of the angle across from it, which is 58 degrees, equals, let's see, which ones do we want to work with here? Let's find Tm, okay, Tm magnitude over the sine of the angle across from it. Okay, well, here's Tm. So the angle across from it is 2 degrees. Sine of 2 degrees. Okay, rearrange, solve, Tm, okay, or cross multiply, or however you want to, whatever you want to do here. Tm is, okay, 144.03 pounds, which I think, I'm going to guess that if we went back over here, we would see the same answer. Where is it? Son of a, okay, let's see here. Tm, 144.03 pounds. Okay, looks good. Okay, oh, don't get ahead of ourselves. All right, and then we would do this again. I would use the same numbers, 3,500 pounds over the sine of 58 degrees, equals, now we'll do TC, TC, okay, the tension in the cable, so that's this line right here. So the angle across from it is 120 over the sine of 120. Okay, so we're going to go ahead and solve for that. And TC equals 3,574.2 pounds. Okay. All right, which I'm assuming is going to match 3,572.4, 3,572.4, 3,574.2. Yeah, okay. I said it wrong. Okay. So I will note also in both of these cases, okay, we're only going to report 3 significant digits, okay? So we kept 5 all the way through, but the way we want to do this, we want to say the tension in the little man tension is 144 pounds, and the tension in the cable, okay, equals 3,570 pounds, okay? And that's what you would report. I forgot what it was we were asking. What are we asking? What is the tension in the rope being held by the tiny man? Well, the answer is 144 pounds of tension. All right, which is actually pretty impressive to pull that to the side, I would think. Maybe not. I don't know. Maybe I'm just weak. Anyway, so that's your answer. Woohoo! And what's cool is you can see you can do it either way. In this case, okay, I think you probably agree that the component method was harder. Okay, so it's nice to kind of think these things through before you do them. My inclination is always to instantly go to component method. You're going to do components so much through your engineering, through your time in engineering, that there's going to be a temptation to always go to components. But there are times when it's going to be a lot easier not to go to components. Okay. Anyway, so let's go and let's do 3D. So 3D, as you can imagine, presents some more challenges. Okay, so I want to note something here. 3 dimensions means we can solve for 3 unknowns. Oh, this one came out a little bit blurry, so I'm going to write some of these a wee bit bigger so that you can see these numbers. Okay, so this is 5.60 meters. This is 3.30 meters. This is 4.20 meters. This is 2.40 meters. This is 4.20 meters. Yeesh, yeesh. Okay, so note, we've got 3 cables here. We know the tension in one of the cables. We know the tension in this cable right here, A to D. Okay, we know that tension. We don't know the other tensions. Okay, so we're looking for the upward force of the balloon on the ring. So basically we're looking for a force upwards here, but we don't know the tension in this rope or the tension in this rope. So we don't know 3 things. So when you don't know 3 things, that means, you can do that in 3 dimensions because there's going to be 3 equations. Some of the forces in the x equals 0, some of the forces in the y equals 0, some of the forces in the z equals 0. Okay. Now, I'm not going to lie here. This is going to be, this is going to take a little while, and it's going to be a little bit problematic. You just want to focus on the trig here. Okay, and that's really, it's not any more difficult than the other problems, just a little bit more bookkeeping, and there's some trig issues. Okay, so let's start by, I'm going to have to do a free body diagram, but I'm going to write out my equations just so that we know kind of where we're going. Okay, so let's see. Okay, so my equations are this. Sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. Sum of the forces in the z direction equals 0. As soon as I know that I'm summing forces, I need a free body diagram. So let's start by drawing our, so again, when we think about free body diagrams, we want something that's going to have our answer. And so what we're asking for here is, what is the upward force of the balloon on the ring? So I'm going to do free body diagram of the ring. Okay, because the ring is also always nicely set up for this. If you can get a ring in your problem, which isn't always going to happen, it sets up nicely for it, okay? So because it's got what we're looking for, which is this right here, okay? The upward force of the balloon on the ring. So I'm going to call that the force of the balloon, okay? Now, these are going to be hard for me to draw. I'm going to do the best I can, and I'm actually going to get out a ruler, or better yet, a Costco card. Costco card will work. Okay, anyway, so, and the reason I'm doing this is because I am not really that great of a drawer. I can in a pinch, however, and I hope that you can too. So what I'm going to do is I'm going to pause this, and I'm going to draw the free body diagram. All right, so I've done the best that I can do here. It's going to look better on the official diagram, so we will use this official diagram to figure out angles and things like that, okay? Because I simply am not going to be able to do a really good job with that. Now, you might be sitting here going, well, Dr. Wagner, my homework, do I need to draw straight lines and things like that? Yes, this took me all of like 30 seconds to do. And I could work, I'll work with these angles as much as I can. Okay, so let's just go ahead and do that to prove to you that this can be done. But this took me 30 seconds. It's really not a huge deal. Before we move any further, one thing that I want to do here is I want to note that we are using a right-handed coordinate system, and you're going to want to get into a habit of using that. So whoever created this problem told me that x is in this direction. They said that z is in this direction, and y is upwards. Okay? And you might be saying to yourself, what does that matter? Can't I just call it whatever I want? You can, but there are places where that's going to be problematic. We're not to that place yet, but we're going to get there pretty soon. So just to recap, right-hand rule, basically you're going to want your fingers. So if you imagine, you use your right hand, and if you want your fingers, if you imagine your fingers pointing in the direction of x, and then you turn your hand such that your palm is now facing in the direction of y, and then your thumb will point in the direction that z needs to. So you'll note that if I put z over here, it would break the right-hand rule, and this would no longer work. Okay, so we do not want to put z over there. Z goes where z is. Okay, so in this case, whoever created this problem kind of did it for us. Okay, so now we want to talk about these angles so we can figure out the directions of these things, okay? So we'll note that where I put x, that's positive x. Where I put y, that's positive y. Where I put z, that's positive z, okay? And where x is has a unit vector I, y has a unit vector j, and z has a unit vector k. Okay, so we're going to split these up into coordinates for all three of these, okay? Because if you look at this, we've got 4 of these, and I don't want to try to draw triangles with 4 forces in 3 dimensions. That is a real headache. We could do this, but I think I'm going to try to avoid that. Okay, so what I'm going to do is I'm going to look at this force by force, okay? And so let's start with the first one. Let's use yellow as a color. And so what I want to do is I want to break this thing up into this force going in that direction, and then let's see, this force going in this direction. Okay, noting that even though it doesn't look like it, because that's all in plane, that this is a right angle. Okay, it doesn't look like a right angle, but it is a right angle. Okay, so in order to get my 1250, which is my hypotenuse of that triangle, I need to know this angle right here. Okay, I don't know what to call that angle, but let's go ahead and see if we can't figure it out. So I'm going to draw this triangle right here. So it's going down this way. It's going over this way. Okay, and here we go. So this is 1250 newtons. Okay, and I know some things. Okay, so I can go back to the original drawing, and I know that this side of this triangle is 3.3, and this side of this triangle is 5.6. Okay, so that is a similar triangle. It is not the same triangle, but it is a similar triangle. So the similar triangle will have the same angle right here, okay, where we've got 3.3 and 5.6, okay? And it's weird because we can't really write units here because, well, we can write units, but then they're not at all the same triangles, right? Because it can't have newtons being, you know, graphed on the same thing as the distances. But anyway, so we want to find that angle. So if I look at this, okay, I've got the opposite of that angle, and I've got the adjacent of that angle. So we need the opposite over adjacent. We need the tangent. So the tangent of that angle, which I guess I'll just call, I don't know, theta d equals the opposite, which is 3.3 meters, over the adjacent, which is 5.60 meters. Okay, so theta d equals, let's see, well, we need to do the inverse tangent of both sides of 3.30 meters divided by 5.60 meters. Okay, so theta d equals, okay, 30.510 degrees. And what I want you to, something that I should note here because, you know, I pause it while I work my calculator on these things. I highly recommend punching these things in your calculators 2 or 3 times just to make sure that you get it right. You know, because I tend to make a lot of errors with this. I don't know if you guys do, but, you know, if you're one of those flawless people, by all means, don't do it, okay? Anyway, so if I take that back up to my triangle, and I'm going to do the force triangle. Right now I've got a distance triangle, but let's do a force triangle, which has the same angles. So here's my force triangle. Okay, and it's got the same angle, 30.510. I'm going to call that theta d. I'm not going to write all that out right now. But this is 1250 newtons. Okay, so if I'm working with that, cool. I can now get this side of this triangle. I can get either side of this triangle that I want. Okay, and so this bottom side of this triangle right here is going to be, well, sine or cosine. Well, we're opposite, so it's going to be the sine. So it's going to be 1250 newtons times this sine of theta d. Okay, which if I plug into my calculator equals 634.61 newtons. And then this side over here is 1250 newtons times the cosine of theta d, which equals Okay, 1076.9 newtons. Okay, so that's the first force that we have now resolved into units. So what I note is that this force right here is right here, okay, and this force right here is right there. Okay, so we have now turned this triangle into its three forces. So I'm going to go down here and I'm going to just start bookkeeping. Okay, so that is the 1250 newtons. Okay, so I guess I'm just going to call that tension D. Okay, so TD. Okay, so we're going to do components. And what I'm going to do is I'm just going to have to keep coming back to this components as we keep track. Okay, so TD equals, okay, note it is 634.61 in the, well, this is the negative Z direction. So I, J, K. Okay, negative 634.61 newtons. Okay. Now, in this one right here, okay, the 1076.9, that is in the negative Y direction. So that's going to be negative 1076.9 newtons. Okay. And this doesn't at all work in the X direction. So 0 in the X direction. Okay. Complicated? Yes. Very complicated. Okay. So let's do tension B. Okay. Tension B equals, okay, we'll go I, J, oh, let's give little arrows, not hats, J, and K. Okay, let's get the signs right off the bat. Okay, in the X direction, it is going negative, right, because it's acting in this direction. Okay, in the Y direction, it is acting downwards. And in the Z direction, it's not doing anything, so plus 0. Okay, so now we have to look at that one, and maybe, just maybe I'll go over to this thing and I'll look at this triangle. So maybe this will help us kind of do this a little bit better. So I've got 5.60 on this side, and I've got 4.20 on this side. Okay, remembering, even though it doesn't look like it, this is a right angle. Okay, kind of hard to see, but it is a right angle. Okay, so if I look at that triangle, if I go down right over here maybe, let's zoom way in and let's draw that triangle. Okay, we've got 5.60, we've got 4.20. Okay, and really, you know, any angle we want is gonna work for this, but I like to make all of my angles go out from kind of the free body diagram. That's usually the best way to do this. Okay, so I want this angle right here. We'll call it theta B. Theta B. Okay, so theta B, well, how do we get at theta B? Well, I know the opposite side. This is the hypotenuse, and I know the adjacent side. Okay, so if I know the opposite and the adjacent, that's a tangent problem, equals the opposite, which is 4.20 meters, and the adjacent, which is 5.60 meters. Okay, so theta B equals the inverse tangent of that, okay, of 4.20 meters divided by 5.60 meters. By the way, if you're struggling with this trig, I recommend pause this thing on all of these and make sure you know how to do this, okay, because the trig is going to keep coming back. Okay, it's going to come back again and again and again and again in this class. All right, so, okay, 36.870 degrees, which means now I'm going to want to kind of get at the forces in this case. So if I do my force triangle with theta B, and this is tension B. Okay, so that's the magnitude of that. Okay, so then this one right here, again, I'm not gonna keep redoing these trigs, but I do recommend that you make sure that this all makes sense to you. So this is going to be tau or TB. Okay, so the tension to point B equals that side is TB times the so this is the adjacent, so it'll be cosine of theta B, 36.870, keeping 5 significant digits, and this will be TB is the sine of 36.870 degrees. Okay, so those are our two sides. Okay, so These are going to go over into our big, nasty equation over here. And so we'll say in the j direction, we've got this cosine, well, how do I squeeze in 36.870, 36.870 degrees. And then in the x direction, we're going to have TB sine of 36.8. Why aren't you writing, you punk? 870. It's too late in the class to be having this problem. All right, so cool, tau b. All right, now we get to the last one, to the one that's going to be the hardest, which is going to be tau tc. Okay, and let's see what we can do with tc. All right, so what we're going to note that makes this one a little bit special, and this is where the 3 dimensions really becomes problematic, is that if I draw, this is the triangle right here, okay, and I note that like the other ones, there's a right angle between here and here, okay, it's kind of hard to see, but the problem is getting the length of this bit that goes along the in the xz plane. Okay, noting that to get to that, I've got another triangle right here, and this is a right angle. Ooh, yeesh. Okay, so I'm going to draw it over here, where hopefully it will make more sense. I'm going to delete everything else. All right, and hopefully, you know, the book drawing here will be better than mine. Well, it definitely is better than mine, but let's focus up here just because. All right, so there's a triangle right here. Okay, I hope that you can see that triangle. And you can see that it is a right triangle, okay? Angle AOC, okay, is a right angle, okay? So we can work with this triangle exactly like we did the other ones, because we know that this side of this triangle right here is 5.60, okay, based on this. But I don't know this side right here, okay, side OC. So in order to get at that side, I need to make note of the fact that this side right here is 4.20 degrees, and this side right here is 2.40 degrees, okay? So if I know those two things, then OC, the length of OC, is going to be the square root, so I'm using Pythagorean theorem here, 4.20 meters squared, plus 2.40 meters squared, square root. Okay, so OC then equals, okay, 4.84 meters essentially. Okay, so that's good. So that's OC. So now I know that this triangle, the triangle that I'm working with here, where this is A, this is C, and this is O. Okay, the bottom side of it is 4.8374 meters. The vertical side is 5.60 meters. And again, I want this angle, okay, which I'm going to call theta C. Okay, so it's going to be just like the other ones, right? Because I know opposite and I know adjacent, so it's going to be tangent. So if we follow the pattern I had right here, I can say that the tangent, that the angle theta C equals the inverse tangent of the opposite, 4.8374 meters, divided by the adjacent, which is 5.60 meters. Okay, so theta C then is 40.821 degrees. Okay, again, keeping 5 significant digits. Well, we're going to report 3, but we're going to start with that many. Okay, so just like in the other examples, okay, I'm going to go down here, okay, and I'm going to say then that, what's going on here? Okay, so, sorry, I had a little hiccup there, and apparently I'm still hiccuping. Okay, so anyway, so we can do like this, okay, and I've got this TC, okay, and sorry, this, okay, and so then we've got these two forces, and they're on funny angles, right? So that's going to be a little bit problematic. And so we can start by figuring out this downwards one, which is going to be TC, okay, times the, well, in this case, this is my angle. So this is going to be TC times the cosine of that angle of theta C. Okay, so 40.821 degrees. Okay, and then I've got one right here, TC sine of 40.821 degrees. Okay, now at this point you're thinking we're home free because you're thinking this is just like the other ones, but it's not just like the other ones, and that's kind of annoying. All right, so I'm going to kind of try to compare these sides here. So this one right here is right here. Okay, so that's cool. That's really helpful, right? That is our number. So if I go over to where I'm keeping track of all the components, that is in the negative, the negative y direction? Yeah, the negative y direction. So we're going to have negative right here, TC cosine of 40.821 degrees, okay, J. Okay. Now the problem here that we're running into though is look at this force right here. Okay, and if we zoom in, okay, that one is right here. It's neither in X nor is it in Y. Okay, it is in both. Okay, so we need to break it down into its components. Okay, so we're going to break it down into a component here and a component here. Okay. So if we note, so I'll do it, I don't really know how to keep this organized. Hopefully your notes are more organized than what's coming out here. But I'm going to take this side and I'm going to put it right on the hypotenuse of a triangle that looks like, let's see, I'm going to basically try to draw this again down here. So let's see, so we're here, okay, tip to tail, and then the hypotenuse is right there. Okay, so the hypotenuse is TC sine of 40.821 degrees. Okay. Now the problem with this triangle is I know this is a right angle, but I don't know any of the other angles. Okay, so I need to get this angle before I can solve this. Okay, so how do I get that angle? Well, I note that the similar triangle, that looks like this, here's the similar triangle. Well, this is 2.40 meters, and this is 4.20 meters. So let me go ahead and get that angle. How are we going to do that? Well, it's going to be the inverse tangent. Okay, so I don't know what to call that theta, that angle. Let's just call it alpha. Inverse tangent, so alpha equals the inverse tangent of the opposite, 4.20 meters, divided by 2.40 meters. Alpha equals 60.255 degrees. Okay, so now we're going to put that back onto this triangle. By the way, I know this is exhausting. This is hard. Okay, no one ever said it wasn't going to be. This is a hard day, especially if you're not up on your trig. This gets really, really problematic. So this side of this triangle becomes the hypotenuse. This is the adjacent. So this is the opposite. So the opposite will be the hypotenuse. Okay, that's the hypotenuse, and now we're going to multiply it by the sine of that angle. Okay, times the sine of alpha here, which is 60.255 degrees. And of course, this looks really ugly, but remember, you have a calculator. This is not going to hurt you to just plug this into a calculator. Okay, sine of 40.821 degrees, okay, times the cosine of that angle, 60.255 degrees. Again, really work with this trig. Make sure you can do this. On a test, I can only give you one of these maybe. Okay, these take too long. Okay, so noting that this force right here, okay, is in the, what direction is that force in? It's in the positive x direction. So we've got TC times all that business, sine 40.821 cosine 60.255. Noting these are being multiplied, I just didn't leave enough space there. And that's in the positive x. And then this force right here, okay, is in the positive z. Okay, so that one is plus TC sine 40.821 times the sine, oh, come on, buddy, sine of 60.255. Okay. Well then. All right. Whoa, boy, that was not what we were bargaining for, was it? Okay, and then the last force that we can get here is we want to drive at the okay, we've got the last force, which is the force of buoyancy or the force of the balloon, which is going to be FB equals that's in the positive y direction, so FBJ. All right, cool, and it's 0 in the I plus 0 in the K. Okay, so hopefully that didn't completely hurt you, but please understand that, this is really hard, okay? So don't, get discouraged if you're like, wow, that is impossible. It is not impossible, though it does look impossible, and it does have its very difficult things. It's a lot of bookkeeping, and you're not expected to just get this right off the bat, okay? Anyway, so we've got 3 equations now, okay? And I will spell them out for you, although we're missing an I. We're missing an I right here, the J's we have, and we're missing a K right here. Okay, so here's 3 equations. We have 3 unknowns, okay? I'm going to write these out. So here's the I equations, here's the J equations, and here's the K equations. And basically, we're going to look for an easy one to solve, and we're going to use that to solve the other ones. I'm going to tell you right now the K equation is going to be the easiest one to solve because it's only got one unknown. Okay, so let's go ahead and do that one first. Okay, so we're going to start with the sum of the forces in the z direction equals, equals 0. Okay, so if I write all these out, I'm going to say negative 634.61 newtons plus TC. Now I'm going to plug those numbers into my calculator because I don't want to write all that out again. And so if we do that, so 0.56757 TC. So this problem all of a sudden is a lot easier. So TC equals 1118.1 newtons. Okay, so that makes our job much easier. So now we want to look at the next one to solve. We'd love it to be the y direction because we're trying to solve for FB. Unfortunately, that even if we know TC, it has 2 unknowns because we don't know FB and we don't know TB. So instead, we're going to go and see if we can solve the x direction. So right here, and I'm going to write all that out. I'm going to need a little bit of space probably. So let's just do it right here. Sum of the f and the x equals, I'm going to pause it and just kind of have it pop up. Again, I'm going to punch all these numbers in the calculator so I don't have to write all the trig out. Okay, so punching those things into my calculator. Again, I always like to keep 5 significant digits even when it's annoying, like right here. We get a very tractable problem, okay? Because I can take TC here and I can plug it in right there. And then, we're cooking with gas. So if I plug that number in and I solve for TB, okay, then I get 604.38 newtons, which is pretty cool, right? So now I got 2 of my tensions. And then the last one is to do this last equation, which of course is going to be the hardest for you to see, but hopefully, you've taken notes so you can see it. So we'll do the sum of the forces in the z direction, the y direction equals 0. And then this one should be able to solve the whole thing, okay? So again, I'm going to pause it and it's just going to pop up on the screen. Okay, almost there, plus FB equals 0, okay? So again, I've taken this whole column here, okay? put the sines and cosines into my calculator so I could have just 5 significant digits instead of having to write cosine and whatever, of all kinds of stuff. Okay, so there we go. And this is what we're solving for right here. And let's see what happens. So I need to plug in TC into right here. I need to plug TB into right here. And we solve. And we get, okay, 2406.5 newtons. And we're only going to report 3 significant digits. So it's going to be 2410 newtons. Okay, pretty cool. Okay. Note this. I think this is something that should be noted. So this is the vertical direction, right? So the buoyant force is pulling up, or the force of the balloon is pulling up. The other 3 forces, all these cables are pulling downwards. Notice they all have negative signs. Okay, if that didn't happen, then something is wrong. Okay, none of these cables are pushing the balloon upwards. Okay, so notice the signs end up being the signs are magic. If you keep with the signs and you do the signs correct, they will tell you a lot about whether or not you made an error. Anyway, I'm 10 minutes over, so I'll try to make that up for you on next lecture. Apologize for going over. I wanted you to remember that this is tough, okay, and you're going to have to work through this, okay? So I'm going to assign some of these, and you're just going to have to fight a little bit. You're going to have to fight a lot, okay? Think about the trig and come to office hours if you need help, okay? And keep working, keep plugging, take care of yourselves. It's a tough time. I know it's hard watching these videos. It's hard for me to make them, but it's got to be terrible if all your classes are watching them. So let me know how I can help. Anyway, take it easy, guys, and I'll talk to you when I talk to you. All right.